I'm going to be talking to you today about SimCenter FlowEFD, and our target audience is actually people that need to do thermal flow simulations and have a technical background, but maybe are not CFD experts themselves. So just a little bit of background on myself. My name is John Oliva. I am a consulting engineer, solutions consultant at Siemens Software. And like I said, today I'll just be giving you a brief intro to SimCenter FlowEFD. So just as a high-level overview to kick things off, FlowEFD is our CAD embedded general purpose CFD tool. So we embed within many major CAD platforms. I will be showing you today in the demo that I have. I have a few little demo videos that I'll be showing, and I'll be running that within our Siemens CAD platform NX, but we also support various other CAD platforms. And with the point being that once FlowEFD is running within your CAD environment, then the tool itself behaves and looks just like what your CAD engineers are used to, or if you are using CAD yourself, it embeds right within that tool and looks and behaves just like what you're familiar with. This slide shows the various capabilities within FlowEFD. So much of this is within the baseline package, but then some of this is also, we also offer add-on modules that offer some of these more advanced capabilities, especially from a licensing perspective. Then reduces the cost. If you're not interested in all of these things, you can just get what is of interest to you. So we'll be talking about some of these things as the demo goes on. The focus of today's presentation will really be on the electronics, cooling, and thermal management side of things. So this is an area that FlowEFD has a particular strength in terms of thermal management of electronic systems. And so even though the workflow is the same for all of FlowEFD, you'll see that we have particular capabilities that allow us to model and analyze things like printed circuit boards and joule heating and heat pipes, and being able to import printed circuit board geometry from electronic design packages, things along those lines. So these are some of our strengths as we compare ourselves to other tools that are out there in the market, and that is what the focus of today's presentation will be on. So the particular example that I'll be showing you is this sensor fusion box. So the idea is this would be used inside of electric vehicle to cool some of the onboard electronics. So this is high power electronics, so we have a lot of heat being generated within this system. You can see it's a relatively small package. The image on the left shows the system next to a can of soda, just for size reference. And then here on the right, it shows in the actual CAD model of the system some of the major components. So really the key point to take away from looking at the CAD model is we have these PCBs up on top that are generating a lot of heat, and they are liquid cooled with a liquid cooling path that flows through a board on top of the PCB and on the bottom, and that's being pumped through with this pump with the liquid coolant down here on the bottom. And in addition to that liquid then passing through these boards that are collecting the heat off of the PCB, it then gets transferred to this finned heat exchanger along the bottom that has a fan pumping air through those cooling fins. So we'll just take a overview look at how we would set this up in FlowEFD and some of the capabilities within the system. So as I go through this, the goal of the simulation, if we were actually looking at this from an actual application point of view, is to assess how well we're able to cool off that system using the fans and the finned heat exchanger that I just described. And then we'll also be doing a bit of a design optimization at the end to look at if we can take that baseline design for our heat exchanger and maybe reduce the mass by eliminating some of the fins on that heat exchanger, or just by moving the fan around to different positions. Throughout all of this, you'll see how the advantages of having the system embedded right within our CAD tool really improves the speed of this whole development process. So that is where we're going to start. So this screen here shows what this would look like. If you're familiar with using NX, you'll see that this looks exactly like NX, just has this extra tab for flow analysis built within the ribbon bar that you would normally see within NX. And then similarly, along the left side, we have this additional tab that allows you to control your FlowAFD model tree. So I'm going to jump in then from here into our first quick video. And this video shows an overview of the CAD model, just giving you a additional look at the CAD geometry that I was describing earlier, but also showcasing then how this looks just like NX CAD, because it is NX CAD. It's not like an emulator or anything, it's built right on top of it. So this is showing the various components within that CAD model. And then of particular interest here, look at that fitting right there. So you see the overlap between the blue piece and the black piece. We're using actual production CAD geometry in this example. We haven't simplified anything like you might have to do in other CFD tools, and that CAD overlap that's there for the interference fit, that's not going to cause any problems with our import into the FlowAFD. So now we're here in FlowAFD. This piece is going to show you the fluid volume that is being used for the analysis. This is interesting because in other CFD tools, you would actually have to generate that 3D solid to import into your CFD tool. Here we didn't do that. We just brought in our mechanical CAD model, and FlowAFD recognized where there should be fluid and where there's not. Here we're selecting which physics we want to include in the model. And so actually, if I just jump back there for just a moment here. Let me just bring the video back here for just a second. You can see that the setup of the FlowAFD model uses these intuitive wizards and templates to help you just go through and select which physics you want to include. So you see in here we are going to be accounting for conduction within the solid metal parts. We're going to have thermal radiation. We're going to be accounting for gravity. And as I said from the beginning, the FlowAFD interface has been designed with the intent that we have a technical audience, usually engineers or scientists that are using this, so they understand what all of these physics are, but they are themselves not CFD experts. So this is intended to be presented in an intuitive fashion so that this makes sense to those non-CFD specialists. So we'll pick up the video again from here. As we go on, you'll see the coolant loop that I was describing earlier. So just like we saw the full fluid region before, here's just the coolant loop being shown. So going through that top side, picking up the heat, going through the bottom cooling fins, recirculating through the pump, and then specifying the electric fan that is going to be cooling all of this. And FlowAFD comes with a library of built-in fan components that you can just drop into your model if you don't already have a fan already picked out, or you can specify your own. And this last piece is showing how we are modeling this air filter on the side of our system using porous media. so that we can account for the reduced drag on the airflow and whatever heat transfer would be accounted for through that porous media air filter. So in that quick little video, we just showcased how FlowEFD in this case is embedded within NX, but we'll also talk in a bit about some of the other CAD platforms that we support. We showed how you don't have to model your fluid volume. FlowEFD automatically detected that. The full setup of the simulation is done through wizards and templates, so you don't have to be a CFD expert to do any of this. We didn't simplify our geometry. We're using actual production CAD, so we can account for or just deal with gaps or interferences that so often we need to have for production CAD models, but we don't have to simplify it. And even though this video didn't show it, because it's embedded right within the CAD model, any geometric changes that you make on the fly are automatically detected and synchronized within your FlowEFD model. Next up, we're going to take a closer look at some of these electronic specific things that I was alluding to earlier. So we're going to look at how we can import our printed circuit board geometry through the EDA import function within FlowEFD. So this video shows we're just starting this EDA import module right within FlowEFD. Once we are in there, we can then import this EDA geometry file that we would have created, or our electrical engineers may have created inside of their design software. In this particular case, we are importing an ODB++ file. And you can see along the bottom of the screen, it's importing that file. This is all real time. I didn't speed this up at all. Once it's imported, you can see along the left side of the screen here, all of the different layers for this multi-layer board have come in, along with all of the components that are attached to that board. There were various filters that are available, so we can choose to ignore small components or holes or any other smaller details. This model level allows us to capture the board at various resolutions so that we can have this trade-off balance between having a more refined model, which captures greater detail, models it more accurately, but then takes more computational resources, or going the opposite way, we can take a coarser approach to it, which is less accurate but speeds up our calculation time. Here we're looking at the thermal map for that board that we just imported. So we see the reference designator for all of the components along the left side column, and then the reference temperatures for those components and their resistances and the power output that each one will generate when in use. The one I want to draw your attention to is this line U5. And that one's of interest because it has the greatest power deposition within the system at 200 watts. And so we'll be looking at that in greater detail, particularly when we get to the optimization portion of this analysis. So now that we've looked at the thermal map for this, we are going to, and we've already imported our board, we're going to then take that and transfer it back to our FlowEFD model. And all of these things then that we've just defined within the EDA import will appear in our FlowEFD CFD model as heat sources and power sources within our FlowEFD model. So here we begin the transfer, and you can see in the model tree for our FlowEFD model along the left side here, the heat sources that have automatically come in to our FlowAFD model. And this really speeds up this whole simulation process as compared to if we were left to model this as manually defining each one of those components, which we could do, but you see how quickly this EDA import allows you to automate that whole process. So just to recap some of that, we showed the Float EDA bridge import for that printed circuit board, the different model leveling choices within there, and the thermal loads that are associated for all of those different components on the board. Next up, we'll talk about what we have to do to mesh this part, this entire system, and look at how easily it is to interrogate our solved model to look at the results right within our model, which again is running on top of NX. So our results are presented to us in the context of our CAD model. So here we are back in FlowAFD. This mesh has already been generated in this particular case, but this is showing the basic mesh approach that FlowAFD uses. So it uses a fully Cartesian rectangular grid of cells. And so everything winds up having like this square, almost like a Minecraft appearance to it. But built into FlowAFD's solver are a combination of traditional Navier-Stokes equation solvers, but also empirical relationships to account for thin channels and boundary layers so that we can get away with using a coarser mesh than maybe a traditional CFD approach. So here, if you see some of these elements that are being shown, a single element can account for both solid, like you're seeing with these cooling fins, but also the gas, in this case, air regions around that solid. And so in this single cell here, we have both liquid and solid accounted for. The full mesh for that heat exchanger winds up looking like that. And then while we are setting up a solve, another advantage of FlowAFD is the establishment of these goals. So these are for the user's benefit, that you can set up certain parameters that you have particular interest in. So we're looking at, maybe we're interested in the temperature of that coolant loop, or how much the mass of that heat exchanger is from a weight perspective. And so we can set up all of these as goals, which we can then monitor during the solve or during our design exploration phases. Now we're looking at the calculated results. So we're looking here at just a cut plot of temperature throughout the system. And again, note that this is all superimposed right on the CAD geometry, and we can use temperature probes to go in and query any particular point of interest to find the temperature of a particular value we're interested in. Here we're looking at flow trajectories through our cooling loop to show temperatures and flow directions, and we can also look at pressure drops. Here again is one of those goals that was established so that we can monitor that goal, that particular parameter during the solve and see how things are converging. And any of those things that we just established, whether that's goals or post-processing results like the temperature plots or probe values, we can include all of those in a nice report that we can then just generate as a PDF or a Word document. And if we then solve various different iterations of the same model, we can quickly generate that same report, so we have this as a basis of comparison to look at our results. So we saw how quickly FlowAFD can mesh a model. Again, we didn't simplify the CAD geometry at all. It can account for all the complexities of the actual CAD geometry. We are looking at the results right within NX superimposed on the CAD geometry, and we can export all of our post-processing through reports or even to Excel to further analyze our data. The last thing I want to touch on are some of our design exploration capabilities. So I've been saying from the beginning that FlowEFD's true power comes from the fact that it's embedded right within CAD. So no matter what CAD you're using, you can set up parametric expressions that drive your geometry, and then we can use that to allow FlowEFD to redesign your geometry to find optimum performance of your system. And so we're going to see that here. We have set up within the CAD model for the heat exchanger these parameters that are controlling how many of those fins there are on each of those sections. So we're going to use that to drive the heat exchanger. And then we also have a dimensional parameter that's controlling the position of the fan to find out where it would be most effective. In this particular case, using our HEEDS multi-parameter optimization, we are setting those all up as our control variables. So we have the 4 count parameters that are controlling the number of fins, and then also the position of the fan. And then as our output here, we're selecting the mass of the heatsink, the overall mass of the enclosure, and the temperature of that U5 component that I had brought to your attention before. We allow FlowEFD's optimization system here to run for a total of 100 different iterations. And it's not just shooting in the dark here. It's using a combination of traditional engineering optimization, gradient-based techniques to guide its search, but it's also using evolutionary computing approaches to help guide that search too, to hone in on what an optimum design might look like while controlling these 5 variables that we specified and monitoring the 2 masses and the temperature that we said were of our interest. In the end, by running those 100 design cases, in this particular example, we found an improved heat exchanger design that has 14% less mass because we found that we could control, or we could eliminate some of those cooling fins while maintaining a temperature for that one U5 component similar to the baseline case. So without increasing our temperature much at all, we were able to reduce the mass of the heat exchanger by 14%. All of that was done automated just by specifying to FlowEFD the parametric expressions that NX had already within the CAD model, specifying which ones FlowEFD could drive and then what are parameters of interest coming out of the CFD solution were. Those 100 designs were run within 60 hours, so roughly a half hour per flow simulation. And again, just recapturing some of the results that we saw from that design exploration activity. So threw a lot of information quickly at you since I've only got half hour here, but just want to end off here by showcasing the other platforms that FlowEFD supports. So everything you just saw here today was in NX, but we also support the mechanical CAD packages of Solid Edge, Creo, used to be Pro-E, CATIA V5, SimCenter 3D, and then we also offer a standalone package. So if you don't already have a 3-dimensional CAD platform to use, we can hook you up with the standalone system, and then FlowEFD will be running on top of its own CAD software that you can do all of these things in that we just described. Any one of those, you will see the seamless continuity that we just witnessed, so that whichever these CAD systems you're using, FlowEFD will have the look and feel of those systems. And then all of that automated pre-processing, post-processing, and design exploration will be built right into the same unified user interface. As I said, I know that's a lot of information to jump through in a half hour. Please take down my contact information. Again, I am in this Center of Excellence for 3D fluids thermal simulation within Siemens software. My focus is on FlowEFD. You can reach out to me via the phone number or email address now on your screen. So here's just one case of one of our automotive partners that was willing to share examples with us. So full vehicle aerodynamics study comparing FlowEFD results to wind tunnel tests. So on all of these charts, they're looking at the pressure drag coefficient for the car. The black diamonds are what were measured in their wind tunnel. FlowEFD is the red line. And so you see pretty good correlation from an overall perspective. If anything, where you see things getting off track are at some of these regions where the geometry is changing very tightly. And so if anything, I think that FlowEFD, because of the way you can see how refined the mesh is at some of these smaller areas, FlowEFD gives the engineers the ability to measure things on a much more refined schedule, on a much more refined manner than what they could in the wind tunnel. And so I'm not saying for certain that FlowEFD was more accurate here. It's just it's measuring on a different scale. So, but from an overall perspective, they found that this was much better than, quote unquote, engineering guidance. And so they could definitely rely on FlowEFD to guide their early design and only have to test a few models at the end rather than all these intermittent models that they used to. So that's one example that I have readily available. But as I say, we have similar case studies from various industries, and then classical validation examples just from, fluid mechanics, flow over a cylinder, flow over airfoils. Those validation examples come with the installation of FlowEFD. Some more applied case studies like this are available on our Siemens website if you would like to pursue those.